ketones are only compounds containing the C double bond O, and this should be alone. But if we have a carboxylic group like C double bond OOH, or esters like C double bond O and another carbon, they are not considered carbonyl compounds. Now, as we said that aldehydes are formed by the oxidation of primary alcohols, and ketones are formed by the oxidation of secondary alcohols using potassium dichromate acidified in presence of sulfuric acid. Now, here for naming, for the naming of aldehydes, we add the suffix al at the end of the name. If we have an aldehyde like HCHO, this means that we are having this molecule HC double bond O and then H. So we call this methanal, as it contains only one carbon atom. It is called methanal. We add Al instead of the E at the end of the alkane. For 2 carbon atoms, we call it ethanal. Then 3, we call it propanal, and so on. Of course, we cannot change the position of the CHO group. It should be at the terminal. It should be at the end of the molecule. We cannot place it in any other place and say that we have other isomers. Okay. Now, for the second group of compounds that are the ketones, in order to name them, we have to remove the E at the end of the name alkane and put on. And of course, since the C double bond O is between in ketones, it is in between 2 carbon, it is in between 2 other carbon atoms, then the smallest ketone that we should have is the propanone. We have only 3 carbon atoms. This is the first member in the ketones, will be the propanone, CH3, C double bond O, and then CH3. Of course, if here we have 4 carbon atoms, we call it butanone, but starting from pentanone, we have 2 different isomers. Either that the C double bond O is present on carbon number 2, so we call it pentane 2-on, or we have the C double bond O placed at carbon number 3, so we call it pentane 3-on. So we have isomers in ketones. Now, in the preparation of aldehydes and ketones, we took last time that when we oxidize the primary alcohols, we get the aldehydes. So, for example, if we start with propane 1-ol, which is a primary alcohol, upon oxidation using acidified potassium dichromate 6, which is orange in color, the acidification is done using sulfuric acid. And as we said last time, we write oxidation O between brackets. This will lead us to the formation of propanal. Of course, here we have to be careful on doing this reaction. In this reaction, as you see here, to obtain only the aldehyde, we have to place the mixture of the primary alcohol and the acidified potassium dichromate in a beer flask shaped or either round flask shaped, it doesn't matter. And we gently heat it, and we put here what we call a still head, and then connect it directly to a condenser in order to condense the ethanol formed. For example, if we started with ethanol, we obtain the ethanol directly by just gentle heating. Because if we do strong heating, this will change the aldehyde formed into a carboxylic acid. If we want to obtain the aldehydes only, we don't have to heat for a long time. As we said before, heating under a flux means heating for a long time. We don't have to do that when we want to obtain the aldehyde. We have to gentle heating only, and we would condense the vapors coming out of ethanol to form the aqueous ethanol at once. As I told you, we don't have to make heating for a long time or strong heating, just gentle heating. And we obtain the ethanol preferably to the ethanol, or the aldehyde preferably to the alcohol, because the boiling points of the aldehydes are lower than that in alcohols. Okay, so here we obtain the aldehyde by just warming, by just gentle heating or warming, and directly distilling the aldehyde produced. In order to obtain a ketone, we have to do the same reaction. And of course, I forgot to tell you here that, of course, we are adding here acidified potassium dichromate 6, and its color is orange. And we know that the oxidation took place when the reaction mixture's color becomes green instead of orange, as the potassium dichromate will be reduced to the chromium +3, which has a green color, as I told you last time. Okay, and the same process is done if we want to oxidize the secondary alcohol to the ketone. We should oxidize it using the acidified potassium dichromate as well. We are going to add here acidified potassium dichromate, which is, as we said just now, that its color is orange, and upon oxidation, its color will be changed to the green color of the chromium ion. And here, of course, also, we don't have to heat for a long time, but even if we heat for a long time, it will be okay, because ketones do not change further or are not oxidized further to anything else. So even either here we heated gently or we heated for a long time, it will not differ, because the only product that we should get here is the ketone. But as we said here, in case of aldehydes, we have to do gentle heating, because if we do stronger heating, the ethanol or the aldehyde would be oxidized further to the carboxylic acids. Okay, do you have any question here?
No.
Okay, now if we want to reduce the aldehydes and ketones, they are going to be reduced back to the primary alcohol. It would be the reverse of this reaction, the opposite of this reaction. We can do it as we oxidize the alcohols, whether they are primary or secondary to aldehydes and ketones. We can return back the aldehydes and ketones back into primary and secondary alcohols by using a reducing agent. So if the aldehyde is reduced, it will return back to the primary alcohol. If the ketone is reduced, it will return back to the secondary alcohol. And we usually do this reduction using either what we call sodium boron hydride or sodium tetrahydroborate or lithium tetrahydroborate. Either this or that would be used as a reducing agent. But here we must use them always in dry ether, in presence of dry ether. When they ask you about the conditions, you have to mention dry ether. Why? Because lithium tetrahydroaluminate is very reactive, and if it's placed in water, it reacts vigorously with water. That's why we have to use both of them in presence of dry ether, as they are powerful reducing agents. Of course, the lithium tetrahydroaluminate is a much more powerful reducing agent than the sodium boron hydride, and that's why lithium tetrahydroaluminate should always be used in dry ether. Now, in that case, we take the aldehyde or the ketone and we warm it in an alkaline solution, an aqueous alkaline solution of either sodium tetrahydroborate, or else we add the lithium tetrahydroaluminate dissolved in dry ether. Either we warm the aldehyde or ketone in aqueous alkaline solution of the sodium tetrahydroborate, or else we add the lithium tetrahydroaluminate dissolved in dry ether at room temperature with the aldehyde or the ketone. Now, as we said before, in oxidation, we write O between brackets. Here, sometimes they ask you to write the equations using this symbol. The H between brackets means reduction. And every bracket containing a hydrogen represents a hydrogen atom, only one hydrogen atom. So here in ethanol, we have to add 2 hydrogen atoms to return it back to the primary alcohol. That's why we put here 2 and then between brackets hydrogen, because we need 2 hydrogen atoms. You have to be careful because sometimes they write the equation of the reduction using H notation. So you have to know how many hydrogen atoms you are going to put here, because here we want to add a hydrogen atom next to the hydrogen and a hydrogen atom bonded to a carbon. So we have to write here 2H between brackets. In case of ketones, the same. We are going to add 2H between brackets to get the secondary alcohol. Okay, now we come to a very important reaction for aldehydes and ketones, which is the nucleophilic addition. Nucleophilic addition in case of aldehydes and ketones. Nucleophilic addition for aldehydes and ketones. Now we have a C double bond O group, which is the carbonyl group. And as we know that the oxygen is a more electronegative atom than the carbon, then it will have a partial negative charge and the carbon will have a partial positive charge. So as we have a double bond, we knew that whenever we have a double bond, then we should call our reactions addition reactions, because all reactions happening on a double bond are addition. Either we have a C double bond C group or we have a C double bond O group, there will be addition reactions. Something is going to be added on the double bond and the double bond should be broken. And as we have here a partial positive carbon, then this partial positive carbon should be attacked by something that is a nucleophile, for example. Of course, it's not going to be attacked by an OH, but I mean that in general, we are going to attack the C double bond O by a nucleophile. And we said before that a nucleophile is something that loves nucleus. Nucleophile means loving nucleus. And so it is loving the positive charge. And this means that it should carry either a lone pair or a lone pair and a negative charge. So this is called nucleophilic addition because the attack is using a nucleophile, which is a species carrying lone pair of electrons and or a negative, not or, and I mean a lone pair and or X minus. I mean by or, it doesn't mean that it is going to be attacked by an X minus only. No, usually the attack should be using the lone pair of electrons. So here, if we have an example, is the interaction or the reaction between the carbonyl group, whether it is an aldehyde or a ketone, with HCN. And this reaction should happen in presence of potassium cyanide as a catalyst. So the nucleophilic addition that we are going to study for aldehydes and ketones is the reaction with the hydrogen cyanide in presence of a catalyst like sodium cyanide or potassium cyanide. Now, as we said in halogenoalkanes, whenever we have a cyanide group, this means that we are going to increase the number of carbon atoms in our chain reaction by 1. So, for example, if I have in general, RC double bond O, and here either we have an H or we have an R dash, if this is an aldehyde, and this carries a partial negative charge, and this carries a partial positive charge. So the first step would be the attack. You see the lone pairs are drawn always near the carbon, not the nitrogen. The lone pairs that are going always to attack the positive carbon should be the one at the carbon atom. You have to take care of such things because they, if you do not do that, they will remove a mark out of you. So here what happened is that the cyanide of the potassium cyanide at the beginning, this is potassium cyanide, its cyanide ion is going to attack the positive or the partial positive carbon, and at the same time, this bond is going to be broken. As I told you before, whenever a bond is formed, another bond should be broken. So here it will form the RCO negative. Now the oxygen becomes negatively charged, and the cyanide group is going to bond to the carbon, and here we have the H, and this is the intermediate that is formed at the beginning. And then comes the HCN, which is our reagent that we added at the beginning. So here comes the HCN, and there the oxygen will attack the positive ion of the hydrogen ion, removing the cyanide ion outside once more to produce the RCOH, and here we have an H, and here we have a cyanide group. And of course, the cyanide ion will come out as it entered. This is a catalyst. At the beginning, it entered cyanide ion as a catalyst, and it is removed at the end of the reaction also as it is added at the beginning and removed at the end, then it acts as a catalyst, which is the potassium cyanide. Okay, you understand this mechanism?
Yes.
Okay, and then as we said before, that this cyanide group could either be oxidized using, it could be hydrolyzed, I mean, either it's hydrolyzed using aqueous HCl. We said hydrolysis means breaking down with water, and in that case, we get the RCOH, and here we have a carboxylic group. Of course, together with ammonia, we said that this bond will be broken, or else we use sodium in presence of ethanol in order to reduce this group and get the RCOH. And here we have a CH2NH2 group. The cyanide is going to be reduced using sodium in presence of ethanol, and we get this molecule CH2NH2. And in both cases, as we mentioned before, the number of carbon atoms that we started with here increased by 1, either by hydrolysis or by reduction. The chain is increased by 1 carbon atom. And this molecule, we call it nitrile. We don't call it cyanide, we call it nitrile. Do you have any question concerning this mechanism?
Miss?
Yes.
Miss, here, can we reduce it by using LiAlH4?
Yes, we can, but it's preferable to use sodium and ethanol.
And Miss, for the oxygen there, isn't the lone pair supposed to be behind it?
Behind it where? Here?
Yeah.
It doesn't matter where you put it. But I put it here in order to show that it's going to attack the H positive. Usually the lone pairs that attack the positive species.
Oh, okay.
If you put it here or there, it doesn't matter. It means that oxygen carries a lone pair of electrons, but where do we put it? It doesn't matter. Okay.
Okay.
So it's preferable to use sodium and ethanol. So here, as I told you here, this is the nucleophilic addition of HCN. If we started with propanal, for example, CH3, CH2, C double bond OH plus HCN, then the oxygen, the C double bond O bond will be broken, forming an OH, and this is the hydrogen, and the cyanide group will enter here, and we call it a nitrile. We will say this is 1, 2, 3, 4. So this is 2-hydroxy, as I said here, if we number here starting from the cyanide group or the nitrile group, then it will be 2-hydroxy butane nitrile. 2-hydroxy butane, because we have 4 carbon atoms, and then we say nitrile. And as I just mentioned, that we can hydrolyze this group using dilute hydrochloric acid and reflux to change it to a carboxylic group and ammonium ion, or else we reduce it using sodium and ethanol to form the CH2 and H2. You see here, upon reduction, we added 2 hydrogens to the carbon, and 2 hydrogens to the nitrogen. That's why we write here 4 and then between brackets H, because we added 4 hydrogen atoms. As I told you, because sometimes they ask you to complete the equations. Now, as I told you for the mechanism, that this is the C double bond O, then the lone pair on the carbon atom of the cyanide ion will attack the partial positive carbon, and this bond will be broken, forming the oxygen lone pair of electrons, which is negatively charged. And then this lone pair of electrons will attack the H positive of the hydrogen cyanide to form the 2-hydroxynitrile. Of course, and the cyanide ion comes out as it entered at the beginning. Okay. Now, there is a very important reaction for aldehydes and ketones that distinguishes them from any other homologous series. And if we have a compound that we are not sure, is it an aldehyde or a ketone or anything else, then this reaction is specific for carbonyl compounds, which are aldehydes and ketones. It will not give a positive result with any other compound. In this reaction, we add a reagent which is called 2,4-dinitrophenylhydrazine. This is the name, 2,4-dinitrophenylhydrazine. Of course, we are going to see its structure now. You are not supposed to know the structure of the 2,4-dinitrophenylhydrazine, but you should know how does it react with aldehydes and ketones. So this compound, which is a reagent only used to test for carbonyl compounds, aldehydes and ketones, is called 2,4-dinitrophenylhydrazine. Of course, phenyl means benzene ring, as we said before. When the benzene ring is a substituent, is named as a substituent, we call it phenyl. And hydrazine means that we have NH, NH2. Okay, the NH2 group is called hydrazine. As I told you, I'm just mentioning the structure of this compound, but you are not going to be asked to draw it. And then 2,4 means that at carbon number 2 and at carbon number 4, we have a nitro group. We say 2,4-dinitrophenylhydrazine. So this is the structure of this compound. Sometimes we write it 2,4-DNPH, means dinitrophenylhydrazine, DNPH. Okay. Now, when we add 2,4-dinitrophenylhydrazine on an aldehyde or a ketone, directly, as you see here in this photo, a deep orange precipitate. It's a precipitate, not a solution. A deep orange or red precipitate is going to be formed. Okay, so this is the structure of the 2,4-dinitrophenylhydrazine. I've drawn it here. It's the same as this one. And sometimes they use the precipitate formed after being recrystallized. It means purified. Recrystallization means purified from impurities. Sometimes they have more than one aldehyde or ketone. Sometimes they have more of one aldehyde or ketone. All of them, if you measure their melting point, you find that their melting points are similar. Sometimes we have 2 or more aldehydes and ketones. This point is not stressed here. They just mentioned it here, but they didn't show, they didn't explain how does this work. Sometimes we have more than one aldehyde and ketone having the same melting points. So using the melting point or measuring the melting points, we will not be able to identify which one is this aldehyde or which one is that ketone. You understand? Sometimes I have more than one aldehyde or ketone, for example, 3 compounds. When we measure their melting points, we will see that all of them will have the same melting point. So we cannot differentiate between them. We cannot say which is the, for example, ethanol, which is the propanone. We will not be able to distinguish between them because the 3 of them have the same melting point. So in order to differentiate between them, we react them with the 2,4-dinitrophenylhydrazine. And the product that is formed here, each product of dinitrophenylhydrazine, which with each one of these will have a different melting point than the other. And of course, we compare it with the references in data booklets to determine which one of them is so and which one is 2 and which one of 3. You understand what I mean? The compound themselves without reacting with anything, if we want to differentiate between them, we should measure their melting point. And from the melting points, we can identify 1 as so and so, 2 as so and so, and 3 is so and so. But sometimes the 3 of them, all of them have the same melting point. So we will not be able to differentiate between them. So in that case, we react 1 with 2,4-dinitrophenylhydrazine, it will produce a compound. 2 reacted with 2,4-dinitrophenylhydrazine, it will produce another compound. And 3 with 2,4-dinitrophenylhydrazine would produce a third compound. And now if we measure the melting points of these 3 new compounds, they will be different. And from data booklets, we can determine which one of them was 1, which one was 2, which one was 3. Understand?
Yes, miss.
Okay. Now, of course, we call the reaction between 2,4-dinitrophenylhydrazine and the ketones or aldehydes, we call it a condensation reaction, because here also a small molecule is going to be eliminated. We stated that condensation reactions are reactions where 2 compounds are added together with the elimination of a small molecule. So sometimes they bring you this thing in the exam. You don't have to know the structure of 2,4-dinitrophenylhydrazine, but you have to know the reaction happening between itself and the ketone or the aldehyde. So here it's very simple. You are going just to remove the hydrogens of the hydrazine group. This is called the hydrazine group, NH2 and H2. So you are going to remove the H2 with the oxygen of the aldehyde to produce water, and just bond the nitrogen to the double bond of the carbon. The double bond here is not going to be removed. It's the nitrogen is going to replace the C double bond O. It's going to replace the oxygen of the C double bond O to produce N double bond C. And this is the orange precipitate that is formed. We call it a condensation reaction, as when these 2 molecules are added together, a small molecule, which is water, is eliminated. Okay. Now, how can we, now we said that in order to know that we have an aldehyde or a ketone, we are going to add the 2,4-dinitrophenylhydrazine, we get the orange precipitate. Now we knew that we have an aldehyde and we have a ketone, but which one of them is the aldehyde and which one is the ketone? Then we have to find out tests to distinguish between aldehydes and ketones. The first test here is using what we call Tollens reagent. Now, Tollens reagent is ammoniacal silver nitrate. It means silver nitrate dissolved in ammonia. And when we dissolve silver nitrate in ammonia, is going to form a silver amine complex, a complex that we call it a silver amine complex. And this is called ammoniacal silver nitrate or Tollens reagent. So when we add Tollens reagent, once to a ketone and another time to an aldehyde, and we just warm them even in a water bath, we will find that the ketone is not going to be changed. Nothing will happen to the ketone. But for the aldehyde, it will form what we call a silver mirror. This is called a silver mirror. The silver mirror means that silver metal is going to be precipitated at the sides of the test tube here. So that's why we call it a silver mirror. So what happened is that in case of aldehydes, when they reacted with Tollens reagent, which is the ammoniacal silver nitrate, At once, the ammoniacal silver nitrate is going to oxidize the aldehyde. The aldehyde is going to be oxidized to the carboxylic acid, and the silver ammoniacal silver nitrate solution is going to be reduced. The silver ion is going to be reduced to silver metal. So this is an oxidation reduction reaction where the Tollens reagent, ammoniacal silver nitrate, oxidizes the aldehyde to carboxylic acid, and itself is going to be reduced to the silver mirror, to the silver metal. That's why it forms what we call a silver mirror at the sides of the test tube. But for ketones, we said that ketones do not oxidize further. Here, aldehydes did this reaction because they can be oxidized further to the carboxylic acid. But for the ketones, they are not going to be oxidized further. That's why nothing will happen if we add Tollens reagent to the ketone. Okay, this is the first test. The second test is adding a solution that we call it Fehling solution. In case of Fehling solution, what is Fehling solution? It is copper sulfate dissolved in an alkaline solution. It's copper sulfate dissolved in alkaline solution. As you see, copper sulfate is blue in color, so this is the blue color of the copper sulfate. And if we added to the aldehyde also, here copper carries a +2 oxidation state. So when it reacts with an aldehyde, then also it's going to oxidize the aldehyde to a carboxylic acid, and itself is going to be reduced to the copper oxide. Here the copper carries a +1 charge. It is reduced, forming a red precipitate. This is a red precipitate. So in case of aldehydes, it will do the same as Tollens reagent. It will oxidize the aldehyde to a carboxylic acid, and the copper ions are going to be reduced to copper +1. And copper oxide, where copper is +1, is a red precipitate. So in aldehydes, we get a red precipitate from the blue solution of Fehling. And for ketones, nothing will happen because, as we said here, that ketones are not further oxidized. So these are the two experiments that we do to test or to distinguish between aldehydes and ketones. Okay. Do you have any question here?
No.
No.
Okay, thank you. Now, there is a reaction that is distinguishable for compounds that have a CH3 C double bond O group. This is only for this group, CH3 C double bond O group. Of course, this could be present in a ketone, but the ketone should have a CH3 before a C double bond O group. If we have a ketone in this way, CH3, CH2, C double bond O, CH2, CH3, it will not give a positive result with this test. This test, we say the formation of triiodomethane, or sometimes we call it iodoform test. Either we call it the iodoform test or we call it the triiodomethane test. Iodoform or triiodo is this compound, CHI3. This is called triiodomethane, or sometimes we call it iodoform. Okay. I don't know if you know, there is something called chloroform. You use it in biology. Chloroform, it's used to make animals or whatever you are going to, what do you call it, tashrih. In tashrih, we use the chloroform to let the animal sleep, or whatever you are doing, sleep. Okay, but this is similar, but using an iodine instead of the chlorine, so we call it iodoform, or else we call it triiodomethane test. This test is specific for ketones that contain this group, CH3 C double bond O group. But if the ketone contains this, something like that, it will not give a positive result with the iodoform test. There should be a CH3 C double bond O. So ketones containing this group, or the only aldehyde that can give a positive test with the triiodomethane is the aldehyde which is CH3 C double bond OH. The only aldehyde that can give a positive test with this test is the ethanol only. Or else sometimes we have a secondary alcohol. We have a secondary alcohol. Also, it will give a positive test with the iodoform, where or it gives a positive test with this test, because at the beginning the secondary alcohol is going to be oxidized to a ketone, and then the ketone would give the positive result with the iodoform test. Okay, so these are the three cases only, because in this type of questions here, they bring you some of the compounds and say, we reacted this compound with the iodine in presence of alkaline solution. Either they write you, it give a positive test, or it no change. And then from different experiments, they tell you, identify compounds A, B, and C. So you have to know which compound gives a positive test with Tollens reagent, which compound gives a positive test with Fehling solution, which compound gives a positive test with the triiodomethane test. You have to know these things, because in these reactions, yani, very rarely they bring it in very simple reactions like that. What does this do? What does this do? Sometimes they bring it, but not all the time. Most of the time, they bring you more than one organic compound. They do different experiments on these compounds, and they tell you from this experiment, deduce the structure of A, deduce the structure of B, deduce the structure of C. You understand? So you have to be very careful when you study these reactions. Now, in this reaction, as I told you, it's characteristic for a CH3 C double bond O group, whether it is present in a ketone or in ethanol or a secondary alcohol. We use two reagents here. We use iodine in alkaline solution. In alkaline solution, or we can say sodium hydroxide. We use iodine in an alkaline solution, and we add the iodine. We add the iodine dissolved in this alkaline solution to our compound. We don't know. We add it to our compound and warm a little. If a yellow precipitate is formed, because this iodoform is a yellow precipitate. So if a yellow precipitate forms, this means that we have this group in our compound, or else a secondary alcohol. Either we have this group in our compound, the CH3 C double bond O, or else we have a secondary alcohol if it gives a yellow precipitate with the iodoform. Okay, so what happens here is, for example, if we have a methyl ketone, as I told you, we should have the CH3 C double bond O. We don't know, yani, the R group means that whatever we have afterwards doesn't mean anything for us. We are just concerned with this part of the molecule. So we added aqueous sodium hydroxide, and we added the iodine. Iodine, this is the iodine, but it's so small. Iodine plus sodium hydroxide aqueous in step 1. So in step 1, what happens is these 3 hydrogens are going to be replaced by 3 iodines, because we reacted here sodium hydroxide with 3 iodine molecules. So 3 iodine atoms are going to replace the 3 hydrogen atoms here in the ketone. And of course, here we get 3 hydrogen iodide, but it's not written because we are not concerned about it. We are concerned only about our product, which is the RCOCI3. This means that 3 iodine atoms replaced the 3 hydrogen atoms here. And then there will be a further step, which is step 2, where sodium hydroxide aqueous that we are using hydrolyzes this compound here between the C double bond O and the CI3, producing the CHI3, which is the triiodomethane or the iodoform, which is a yellow precipitate. And the rest of the molecule is going to form a carboxylate ion or a carboxylate salt, because we are using sodium hydroxide. That's why when it is hydrolyzed, it produces RCOONE, the sodium salt of the carboxylic acid. Okay. Also, as I told you, if we have this group, which is the secondary alcohol, we can test it by the same way. We are going to add iodine in presence of sodium hydroxide and warm a little. Also, it will give us the yellow precipitate of the triiodomethane, of course, and the rest of the molecule is going to be oxidized. If we want to change this back to carboxylic acid only, we just reacted with any acid. So it will form a salt sodium chloride, and the H positive will substitute the sodium ion to get the carboxylic acid. Understand, or shall I explain it once more?